Okay, good afternoon. We're going to see today some recipes for voice cloning for data scientists. This was an idea that we had working for internal projects for some customers that needed this type of services, and we thought it's useful to share a little bit of our experience. As a disclaimer, we're not deep experts into voice synthesis nor voice cloning, but we have some experience in tools that can be used to reach these goals. Okay, so let's go. Voice synthesis. Why is it important? Well, this means the ability to make a computer speak or to make a computer understand the sounds that we are producing. And why is it important? It's one of the first applications that come to mind is accessibility. This means the practice of making your website usable by as many people as possible. Another side of the coin is convenience. This will benefit not only people with disabilities, but also make sites accessible for other groups, such as those using mobile devices or those with slow network connections. Therefore, these two are not necessarily different, as I said, but they can be convenient one for the other, and just voice synthesis is just an assistive tool. And what is this? Why is it important? How do we perceive it? Well, this is a long time dream of humans. Humans have dreamed for this, and this is shown in voice computer systems from Star Trek, from HAL 9000, and so on. But it's also, besides a dream, it's a necessity. When somebody loses their ability to speak, they also lose this way of interfacing, not only with computers, but with other people as well. Here is the example of Professor Stephen Hawking, who lost his ability to speak in 1985. But how does this work? We humans, we think in language. We imagine our thoughts, but what comes out of our mouth is not text, it's a widely different format. How well can we define or understand the rules that govern human language and speech? This is the main question. So our brain can translate very rapidly between the two. The challenge is to get a computer to do the same in order to build what we probably heard as text-to-speech and speech-to-text systems. So systems that are able to translate from waves to letters and or ideas that we have. Our presentation is about synthesis, but it's more specifically about cloning. There has been a lot of craze lately related to cloning and deepfakes, mostly related to animating a face in a very believable way. We here care about voice cloning, which can be thought as a subset of voice synthesis, where the resulting voice is modeled on one specific voice, recognizable enough by other people as somebody's voice. In this example, we can see two voices, or in the above picture, we can see two different voices represented by different colors. And this idea of voice cloning comes with its own unique advantages. There are applications where you can paste in an additional word after you finished your recording, or you can correct a section without having to re-record. And this is very useful for podcasts. Movie dubbing could be done in an original actor's voice, and this can be used for movies which currently are translated by a human process, quite costly. And your business could have an already recognizable voice. Therefore, you would like to want a chatbot to speak to use that voice. So moving on, And thinking again about Professor Hawking, he was given a synthetic voice that was robotic enough that he could associate with, even refusing to upgrade it to a more natural one in later years. But if we could, it would be more preferable for such an assistive system to be able to speak in the person's own voice to begin with. Now, let's see how can we build, or what are the building blocks that we have in order to build such a system. What we perceive as audio are waves, a continuous fluctuation of motion of the air around us. But computers can't really model that. We are using digital signals, not analog signals. So we need to take discrete samples of the amplitude at a set of time and set some intervals of time. So as you may know, what we have to work with is an array of values. The quality of a signal is given by how many times per second you take samples and how much information you save at each sample. It's just like when working with images, a pixel value tells you nothing without taking into account the surrounding pixels or a sequence of values in time. To us, likewise, a single sample tells us nothing. It could have been caused by any number of combining frequencies. When what you need actually is to aggregate information over a small window of time. Just in the same way a kernel in a CNN aggregates features in the data that are closer together, in our case, closeness is not defined by pixel proximity but by time. So a sliding window bits of information, and via Fourier transform, we get a heat map of component frequencies in that timestamp. This is called the MEL spectrogram that we're looking at, and it's a meaningful way of structuring audio information. Putting them side to side, and you'll have an image that meaningfully represents the change in the frequencies. So how do we make a computer learn a cognitive task? Let's get back to the task at hand. How do you make this device speak? Well, deep learning is definitely the answer to this problem. But in this image, it's funny enough, but that's a proposal of somebody that would like to use machine learning for determining if a number is odd or not. We've been doing this, or trying to do at least, for the better part of the last century. Remember that Professor Hawkins had a voice synthesizer without even having the tools needed for a deep learning solution. As in all fields where AI is making a difference, we need to understand the ways we did this before deep learning was possible. Linguistics and signal processing are two fields which comprise much of the needed domain knowledge for us to teach a computer how to speak or how to speak well. And let's take a look at some challenges. Why is voice synthesis a hard problem? Mostly because human speech and language is a very complex and not fully understood concept. A large part of the issues come from the vast differences between these two mediums. First, we have the letters and waves. In each language, there is a natural correspondence between a written letter, or linguists call it a glyph, and how it sounds depending on the context. English, for example, is terrible for this. The first two letters in hello are pronounced completely differently if they were to represent the word he. This is why phonetic symbols exist. To disambiguate between these, um, we can look at the two problems that linguists have. text to phonetic or grapheme to phoneme is first and one of the biggest problem that exists, and there can be different mappings between these from language to language, from accent to accent, and even from speaker to speaker, as we can see here. And words are simple to map. In our text communication, we often have symbols that are shorthand for other concepts. There is a rabbit hole of these inconsistencies. So, for example, let's take here the percentage sign and the dollar sign, which go on the opposite sides of the numeral, but they are pronounced after it in a spoken language. Or if we take the dollar and the K, we don't say dollar 100K, we say $100,000. So, as you can see, many rules. And speaking about numerals, these need to be unpacked differently from context to context as well. 101 future historians can be imagined that enrolled in a history one-on-one class. The same numeral is read in different ways. Abbreviations are a league of their own, differing from it if they're pronounced using the initial spelled out or in a single word. UNICEF, NASA, UNESCO, FBI, CIA. How do you know? How do you know which is which? You don't. You either keep a list and take a wild guess, or you write a convoluted heuristic that checks how pronounceable an abbreviation is. And of course, they vary from language to language as well. So you need to keep a separate list for each language you care about. For instance, SUV is usually pronounced different in English or than in a Latin language. And on top of everything, we have prosody. Prosody deals with how our voices sound, and these sounds depend on the speaker characteristics like voice, age, smoker or non-smoker, etc., or how the speaker is feeling, or on the purpose of the question, which are the factors that influence all these. And everything together is influencing the phasing, the intonation, the duration, and the pitch, for instance, in uneven ways. So let's see how we can tackle voice synthesis. And first, I'd like you to take a look at the two main historical approaches, which are formant synthesis and concatenative synthesis. Formant synthesis, or called also rules-based synthesis, generates artificial robotic sound speech that would never be mistaken by a human. However, maximum naturalness is not always the goal of a speech synthesis system, and formant systems have the advantage that are very intelligible. They can even be used at very high speeds, even though they sound robotic, and this will help, for example, visual impaired to quickly navigate computers using a screen reader. On the other hand, the concatenative synthesis produces the most natural sounding synthesized speech. However, differences between natural variation in speech and in the nature of the automated techniques for segmenting the waveforms sometimes result in audible glitches in the output. Well, we're not going to analyze in depth format synthesis as it deals with modeling speech in its purest form, and it's a quite complicated process. But this is, briefly, this is done by analyzing which frequencies and acoustic features produce certain sounds. On the other hand, the concatenative or unit selection synthesis can be very simple. We need a database of words that can be suitably combined. This is a relevant example for a messaging system in a train station where the voice can announce the movements of trains only by combining a few elements, like in this example, right? For a computer, this looks like a series of waves. And this approach can give natural sounding speech, but several limits of the variation of speech you can generate, and it's good only for niche use cases. It, however, shows us how generalistic text-to-speech systems can be created using a unit selection by going deeper than the words. And here is an example of how you would segment a series of phonemes. And this example, by the way, is from Apple, the history of series voice construction before entering into this natural voice that they have now. And here they even cut the sound, the wave, by half phones. And in the next slide, we can see that these are combined such that perfect or a very um, accurate voice is generated. This is a maximum flexibility that we can get, but there are two main costs to pay here. At the runtime, you need to find the segments that best match the desired utterance with the appropriate prosody, and also need to check if the two segments that you're trying to concatenate fit acoustically next to each other. So this is a real problem. And therefore, what what researchers try to do is to build such a system from different other subsystems. And here we can see this as two main parts, the front end and the back end. And the front end deals with two other major subtasks. First, it converts raw text containing symbols like numbers and abbreviations into equivalent written out words. And this process is often called normalization, preprocessing, or tokenization. And the front end then assigns phonetic transcriptions to each word and divides and marks the text into prosodic units. Phonetic transcriptions and prosody information together make up the symbolic linguistic representation that is output by the front end. On the other hand, the back end, often referred to as the synthesizer, converts the symbolic linguistic representation into sound. In certain systems, this part includes the computation of the target prosody, which is then imposed on the output speech. The front-end operation requires extensive domain expertise and needs different rule sets depending on the language, leading therefore because of this to some strange or brittle design choices. Luckily, we know that we have deep learning that comes to the rescue. And how can this help? Well, first question would be, what's the state of the art? We can see here we identified and we leveraged two tools. One is WaveNet from Google, a deep generative model of raw audio waveforms, which are able to generate speech which mimics any human voice and which sounds more natural than the best existing text-to-speech systems. However, while it produces great results, WaveNet is seen as a black box, lacking the fine-tuning abilities for the control of the end result. It also requires conditioning on linguistic features from an existing time to text-to-speech front end, and thus it's not end-to-end. It only replaces the vocoder and the acoustic model. Therefore, Google built Tacotron, which represents an improvement because we get to apply it and fine-tune deep learning for each of its components. This is yet another black box type model, but with a better separation between its building blocks. And then we have the eternal choice between build and buy. Well, if we think about buying, we have all those alternatives that are on the market, from the main cloud providers to private companies or startups, but all these have the related costs and licensing attached. So we focused more on how to build a solution by using our own data. And there are several methods, as I mentioned a few before, WaveNet and Tacotron. And let's see how we can use Tacotron to synthesize a voice. Anna, if you'd like to take it over and explain um, Tacotron.
Okay, I will try. So Tacotron is an integrated end-to-end generative text-to-speech model. It takes a character sequence as input and it outputs a predicted spectrogram representation. In order to train your tachotron, you need to prepare some pairs of speech and transcript and send it to the system. However, it will not understand directly audio files, but it can understand spectrograms, which are transformed waves. And you train your tachotron using these kind of pairs of spectrograms and transcript. Okay, Tacotron model is also an end-to-end speech system, and it produces mail spectrograms from an input text using an architecture composed of an encoder and decoder layers. The backbone of Tacotron is a sequence-to-sequence model with attention. The encoder part of Tacotron is in charge of the sequential representation of text. Encoder model converts the input text into numbers which the computer can understand. The attention model makes the appropriate connections between the encoder and the decoder. The decoder is an attention decoder and it converts the numbers, converts from the input text back into a form of spectrogram. The decoder consists of multiple neural networks and it creates the next spectrogram using the previous spectrogram through a decoding process. However, we are not able to hear spectrograms. We still need a step. In the following slide, we will see it. So we have the spectrograms, which represent the voice, but we need to transform it into a waveform. And in order to do that, you may use WaveRNN, which is capable to create this waveform from spectrograms. It's a single layer recurrent neural network with a dual softmax layer. And for audio generation, it is designed to efficiently predict 16-bit raw audio samples. It infers a waveform out of the mass spectrogram that is the output of the synthesizer. Should be mentioned that the output must match the output of the synthesizer. And as any deep learning model, it has to predict something. The prediction of wave RNN is the probability distribution of the target sample using the previous sample. And now I will let Calin take the lead.
Very much, Anna. As we discussed, and the title of this is, we want to talk about voice cloning, right? We care about which specific voice you clone. We talked about synthesis. So cloning is a subset of subset of synthesis, where the goal is to create one voice that's recognizable as somebody else's. If you remember how to train your tachotron, you need speech-text pairs, which that's the building block. You're trying to get, when you're inferring it, you're trying to do it in reverse. So these are your pairs. The first question that you have to pose yourself is, do you have a lot of data of the same speaker? Because if so, your system, your deep learning system, will produce a voice clone. The system trained on only one voice will naturally only produce that voice. So this brings us to the first recipe of the day, a gourmet voice clone a la carte, just like the ones you'd expect to get from Siri, Google, all the big names. You do need plenty raw material for it, so at least 20 to 30 hours of voice from your own voice actor. Ideally, these would be cooked following the exact transcripts you already have, so the correspondence is perfect. And you better have a commercial kitchen with 4 or 5 GPUs that you're ready to run on full blast for a couple of weeks, that you don't care about the cost for. So in this example, which we're about to hear, it comes straight out of Microsoft's Azure's solution for this. Oh, sorry, that's not it.
Here's the forecast for the next 4 days.
So, it could come from a human. It has the right intonation. It has the right inflections in the voice. It's a bit happy for a news forecast, but we'll get to that a bit later. This uses the Azure Cognitive Services ARIA voice. But yeah, sure. Big movie studios, such companies will pay for this. They will have big data sets. They can afford to throw GPUs at the problem. For example, for the case with movie dubbing, where you care about replicating one specific actor's voice. Where does that leave most of us? There are plenty open corpora with pre-recorded text-speech data, or at least with speech data. And these have hundreds of hours of people speaking, usually out of copyright materials, so in the form of audiobooks. And they're great. They're LibreSpeech, VCTK comes from Voice Cloning Toolkit, MAI Labs has multiple languages. You can find a good corpus that has kind of speech data that you're interested in. And this solves one problem, but adds another one. Training it will create a mix, or it will average out all the voices. And voice cloning, this is not anymore. It will be good voice synthesis, but we don't care for that right now. The thing we're looking for in this case is called a multi-speaker TTS, as opposed to single speaker TTS, which is any synthesis, right? The main focus is carried away from your target voice. So how do we get this? What are we missing? Again, remember the speech text pairing. The more the merrier, of course. If you train on a single huge data set, you do get the voice you're trained with. We established that, but you need money for it. And we want that, right? We want the target voice, a specific voice, but we don't have this. So it just so happens that we have this, as discussed. So how do we bridge the gap? No surprises here, of course, deep learning. Instead of just speech text pairs, we need to feed the model information about the speaker. But labeling them won't do what we want to do with it. It would more or less be like training two separate models. What we want for our next recipe is a way to describe the particularities of the speaker, to get meaningful cross-learning between the speakers. And we need an indirect way to describe such particularities in the same vein as us humans would to describe as pitch, cadence, coarseness of voice, style of speaking, and so on and so forth. And if this sounds familiar, it's because it's a well-understood concept. Such a reduction in dimensionality is super common in security systems, because you don't train a model on to classify your exact fingerprint, right? You'd have to ask the user to make 1 million copies every time they change their phone, 1 million scans. And what you need to do instead is you need to train an encoder that is very good at telling you how close the two fingerprints are. And in that way, you just keep a few of them, which you know reduce from one user. When a subsequent one comes in from the scanner, you can compare them in distance. Because it's a reduced dimensionality space, you can do Euclidean distance or something else. And is it close enough? Then you're in. If it's very far, you're out. If it's kind of close but not really, this is where it's interesting. In designing these processes, you ask for a password anyway. If the user knows it, the ambiguous fingerprint is added to the data set, and you retrain your encoder to understand that new dimension. Why wasn't I sure of that difference? And we'll get to that for our voices in a bit. So yeah, this is exactly the same thing as we need for voices. Instead of a fingerprint to tell users apart, we want a voice snippet to tell speakers apart. And again, no new concepts. There's voice recognition systems, and they have been for a while. Same thing applies. More data you train it on, more variation in the training data sets. As long as you're sure it comes from the same speaker, the better you're able to generalize over these dimensions and have accurate and meaningful clusters. There's a paper from Google that explains a tailor-made loss function for this exact purpose. It's quite a recent one. It's called generalized end-to-end loss. We'll refer it as G to E throughout the deck and the rest of the presentation and workshop. Oh, fun fact, this is exactly how Google can tell members of your family apart. So when you tell it to play some music, it fetches your Spotify recommendation, or you ask it, how does my day look? It tells you stuff about your calendar without you having to tell how does my specific calendar look. So it's a nice little fact that we can use this for the speaker recognition for something else. Let's go to Anna so she can tell us more about how the encoder does it.
So we have the speaker encoder, and we will discuss few technical bits. Basically, GE2E trains on a large number of utterances for a large number of speakers. For example, we can have n speakers, and each speaker can have m utterances. The extracted feature from the utterances is fed into the LSTM network that we see on the diagram. The last layer of the LSTM network is a linear layer that does a transformation of the last frame response of the network. The output of the entire network represents the parameters of the neural network, such as the utterance, the parameters of the LSTM, and the linear layer. The embedding vector is the normalization of the network output, and it represents the embedding vector for the speaker. Then, a similarity cosine matrix is built with all the centroids for each speaker, built using the embeddings for each speaker. The scope is to make the embeddings from the same cluster distance small, and the distance between other clusters as big as possible. And we will have some slides that will help us understand this. It's good to mention that for this encoding part, we do not need text transcripts. And we can gather a lot of speech samples. For example, we have with light blue for uteruses, for a speaker, with red 4, and with darker blue another 4. And we will see how this happens. So we see here, let's assume that our embedding vector has only 2 columns, one for coarseness and one for pitch. And we have this plot, these results, and what we can see is that in the following slide, for example, we can see that there's a mismatch between some utterances from the dark blue with the light blue color speaker. So this is where GE2E pushes the embedding towards the centroid of the true speaker, and it does that. And more importantly, it pushes away the embedding from the centroid from similar but still distinct speakers. This way, the network learns how to differentiate between aspects that are inherently harder to separate. The result should look like this. We should have 3 different clusters. From here, a simple KNN would give us a speaker verification system. But we already have enough for our multi-speaker TTS. We have the utterances, we have pitch values, we have coarseness. However, the real embedding vector has 256 values. And the encoder, this encoder that allows us to create the clusters, has a pre-processing step and is formed by extractions of MEL spectrograms. It trims long silences, it removes pauses, it's normalizing the volume to a certain value. One may use an already trained GE2E like we did in our work, or may want to train a new data set, and that would require to train on speaker identification and sound bites, form batches of the same length segments in case of the text-independent speaker verification. And the output would be a multi-layer LSTM using a loss function, the similarity matrix for each batch, and would output vectors for each speaker with a length of 256 values containing all the voice characteristics.
Right. Thank you very much, Anna. Now I want to tell you a bit about another paper from Google and the great and very popular repo, as you can see from all the stars and forks it has, that you should definitely check out if you're interested in this, if you haven't already. We're going to use it extensively in our workshops, because the advantage is they also kindly provide independently trained models for the encoder, for tacotron, and for the vocoder. Corentin Jaman implemented Google's paper that it's called speaker verification to text to speech, and it deals with exactly this, as in how can you collate, how can you concatenate the speaker embedder with everything else that you train tacotron with, in order to abstract away a speaker identity as what we'd call a unique voice, and for you to be able to pick and choose and create those specific voices back. So yeah, we're definitely going to use this speaker encoder because it's been trained on 8,000 plus speakers for 3,000 hours, and you can too as well, of course. The paper deals with coming up with a good multi-speaker TTS in a very data efficient manner. So what we discussed earlier with cross-learning between the speakers and the ability to do that in the first place is you do that by conditioning it on these, more than just the spectrogram transcript pair. You concatenate, as I said earlier, you concatenate the fingerprint or embedding of that specific spectrogram in order for you to be able to pick it out back again come inference time. This is a true multi-speaker TTS, which is able to generalize what it learned from one side and apply it to the other, which is greater than the sum of its parts. So it's better than if you would have trained it independently on each speaker that you had. And what's absolutely great from this is the fact that the GE2E loss and the embedder trained using it, they're trained on such a great variety of speakers that it very well describes the latent space of speaker characteristics that we just discussed, and voice variation and so on and so forth. So not only can we clone one of these voices, we can interpolate between them and create new ones, never before heard ones, using random encodings. Kind of like this person does not exist website, if you know it. Well, that uses cans, but I think this voice belongs to nobody.com is not yet taken, so you guys might want to go into that. Okay, forget the randomly initialized embeddings. What's very cool for this is that we can reproduce out of sample voices of people that we can get an embedding for, because we do care about cloning. We will show you the full repo in a collab notebook later on. But now we just want to show you to the second recipe of the day, the Spartan voice clone, which is a fast food favorite. You do need a bit of initial investment if you don't have a pre-trained model, or if you want to make it yourself. But we make the franchise take care of that. We just deal with the fast food. Then you're free to dish out endless amount of voices really quickly, really cheaply, with just about 5 seconds of voice needed for an accurate encoding or reliable encoding. The downside is it tastes very bland and the quality is poor. So, for example, this would be the reference utterance that we create the embedding for. So this is a real person speaking this.
They left him then, for the jailer arrived to unlock the door and escort them to the office.
And if we were to feed this into the embedder and collate that and infer a different text with our forecast, it would come out like this.
Here's the forecast for the next 4 days.
Again, similar to this.
They left him then, for the jailer arrived to unlock the door and escort them to the office.
It's very robotic and not natural.
Here's the forecast for the next 4 days.
So yeah, we need not be disappointed by the word quality yet. Zero shot anything is hard. It's more of an academic endeavor for now, and it's just very good to show us the extreme end of the trade-off between input data and quality. The most important is the absolute reduction in the need for input data, which allows us, if you remember back from the point that Radu made about cloning somebody's voice, for example, in the case of Stephen Hawking, Somebody who loses their voice doesn't preemptively record 20 hours of speech of their own voice, right? You might have to work with a recording of a conference or whatever. And given the fact that if you're able to create a quality voice with just from an embedding, that will be a foundation for later work to try and get that voice to be better. But for most cases, I think you might actually have that data. If you went to 3 or 4 conferences, you will have some data. If you have enough audio data, well, if it's not that much data, we can try and annotate it. We'll also have a notebook with some tips and tricks on data annotation and processing pipelines, which is going to be relevant for this. So yeah, we'll see how to make most of the little data that we have. So stay tuned for that. We saw the 2 extremes of recipes. So can we combine them in a meaningful way? And yeah, of course, the plan is to leverage the abundance of the existing speech corpora and also paste in whatever data we have from our target speaker. So just put it there. Naturally, if you train it from scratch, it will train proportionately more or less to the data that it has. So voice in the bending of a target will have less resolution, but better than on its own because it's helped by all the other data. But now you're getting into the issues of this is still very slow. We're talking weeks on GPUs slow. So we're going to use, we already have implementations on this part. We already talked about that React Reco. So Corentin J's implementation of the paper also provides a pre-trained tachotron that deals with, like, collates an embedder that we have and is trained using the pairs of, not the pairs, but the tuples of embedding text speech. So that's great, which means your time and budget doesn't need to go there. It can all be focused. If you have a finite amount of time and budget, you can all focus it on starting from this checkpoint, and you continue training it on your data for an additional how many iterations you have the time and money for. This brings us to our final recipe, the home-cooked meal. And of course, some ingredients will be pre-bought. It won't be as good as gourmet. We won't even compare, but we don't care. We like it. It's made with love. And you need the same ingredients, the same basic ingredients for the fast food one, but also a bit of extra spice and extra data from your target speaker. And this is, with the amount of data, it's reasonable enough to train overnight around a couple of days on CPU. Again, if the less data you have, the less sense it makes to train it for thousands of iterations. There's a diminishing gain there. But yeah, however many voices you can get, even 10 minutes, let's say for at best 20 to 30 minutes, will get you a way better voice than nothing. So again, with our reference,
They left him then, for the jailer arrived to unlock the door and escort them to the office.
the robotic fast food,
Here's the forecast for the next 4 days.
and our home cooked.
Here's the forecast for the next 4 days.
And if we were to try and play them back-to-back reference and home cooked,
They left him then, for the jailer arrived to unlock the door and escort them to the office. Here's the forecast for the next 4 days.
you can kind of see how it picks up not only the accent, but the kind of cadence to the words that the speaker has, which is great. Again, this is just a very quick visual comparison of, in short, we recommend the home cooked meal. If you're not able, or if your use case calls for a gourmet model, by all means. But it's the case of if you don't know you need it, if you need it or not, you probably don't. So just for small projects, it would be way enough to just deal with the home cooked model and continue training from one of the pre-trained models that are available, either from the repo that we showed or from other repos from NVIDIA or others. That was our slightly long intro, but we're going to get into workshops that we promised. We're still going to have some slides though. The first one will deal with the speaker encoder because we consider that it's such an integral part of that, creating that latent space is important, and we want to see where that comes from. Just play with it more and more, because the better your encoder, the better your way of describing all of the things that define a voice that you can't put in words. So yeah, all of these, train it, make nice, neat clusters. Of course, we're not going to train it now. We don't have time. We need that. And let me just move and bring this. I have it preloaded, just so we don't have to wait for all the imports. It's quite a simplistic thing, and lots of code is poached from other repos, but you'll find links here. And if something isn't clear where it's, whether it's written by us or taken from somewhere else, please do let us know, and we're happy to help you out with this. This is a scenario you'd most often find yourself in. So you start from a video or one long form audio file, which you don't have necessarily sections to it. You don't know who's speaking when. Sorry, just give me a second. Oh no, what am I doing? I'm in the wrong tab. Disregard that, please. I just said we're going to talk about the speaker embedding, so we're back here. I hope this is still loaded in memory. Oh yeah, lovely. The most important thing with the embedder is to load your pre-trained model, of course, from CurrentNJ, or if you want to train it yourself, it's a bit of a headache. You need to source all of your tens of gigabytes of data sets. And what we're going to do is because the vector is 256 long, we can't visualize that. We need a way to take points in that manifold and reduce them down to 2 or 3 dimensions. You can use principal component analysis for this, or UMAP, or any other way of reducing information. And hopefully, after our data set that we preloaded from LibriSpeech, which is one of the corpuses that we talked about, should be this one, I think. You're going to see that we have about 10 folders. These numbers are actually speaker IDs from that wider data set that has hundreds of distinct speakers. What we do is we run all of those through the encoder, and you'll see how they neatly arrange into groups. The more embeddings, the more slightly distinct embeddings you have on them, the better. Because in the side project that CurrentNJ made with just the encoder and funny things you can do with it, contains some speech of Trump where we threw this in as well to see here. What you can do here is I can start speaking into my microphone, which I really hope isn't hogged by Hopin fully, and I really hope this still works. But after I do this and we wait for it for a minute to compute my embedding, I should be put somewhere in there. So I can start. Okay, good. That's my voice. Totally sounds different than how it is in my head. If we run this cell again, and we do it again, I'm gonna try and think of something to say, but I'm gonna say that I really hope that the next embedding that will come out of here will be close to mine, because otherwise all this will fail. Yeah, so you can see I'm only gonna do 2. I'm not gonna keep you for more. I'm quite happy that I'm starting to form a cluster, but as you can see, it would already know with an algorithm. It would tell if this was not a pandemic and we would all be in a room, would try and switch places at the microphone to see this happening in real time. Just quick disclaimer: this will not work that well on crappy laptop microphones. The embeddings will cluster together because of the way the microphone distorts them. So you do need a good microphone for this, or to upload a specific file. If you just give me a second to go back to my slides. Another very interesting thing that you can do with this, which will help with the next workshop that I slightly spoiled by going into it first. Well, we see how you can do speaker diarization. So as I was starting to talk about a long form audio information or an interview or something like that, it might just be the case that you have multiple speakers intervening on each other and just speaking over each other, or you have this bit of text where person one speaks, this bit of text where the other person speaks. The only thing that you need to do is you need to identify those bits, like all the examples of the speakers that are in the video, and label them properly. And unfortunately, without audio, because I couldn't figure out how to run this, but this is in the repo. This is in the Resemblizer repo that you can find this exact example. If you run it continuously on a sliding window of time, and you compute the relative similarities between your reference embeddings and the sliding window embedding, what you can do is you can nicely plot who's most likely to be speaking. So this is from I think Hot Takes interview with Tenacious D. And you just define yourself some boundaries, and you know for sure that the person that you tag as run events is the one speaking, because it's the embedding is mostly similar to that one. And I really get the audio for this, but unfortunately we're gonna have to just look at the graph for a minute. It does work, and it does work in real time. It's quite nice. So the first step you do is you'd run this, you take a profile of your long form audio, you'd cut the bits out. Let's see that in a second. Our second workshop, in our second workshop, we will deal with data processing. Again, an example of a file that I just talked about. Again, array, but they're horrible to visualize, so we're going to stick with waveforms. In a perfect world, this would be from a single speaker and recorded in a studio, so you don't have weird glitches. But we have to deal with messy data as data scientists. So the speaker encoder can do this if you run it on a small window. I have a nice visual for what I just showed you. You neatly map this out over your whole file. You take the bits you don't care about out. You only keep the data from the speakers you need. And now you have audio data from a single speaker. Remember the fact that we train on speech-text pairs. The question is, how do we get the text? As Radu mentioned, the other way around with the thing is, you can start doing it manually, right? And that's what we did for some bits for playing around. But are you sure you have the time and will and patience to do it? No, I don't think so. So to get the data that we need for training a text-to-speech system, we're gonna use a system that does speech-to-text. And for this, of course, you have all your usual suspects. You have Microsoft Cognitive Services. You have Google Cloud. Amazon Mechanical Turk is a great option for this, that people with training TTS do constantly reference the fact that it's good, because it's still a human in the machine. Because either with Azure, the Azure Cloud, and the API, it's dead simple to use. You just plug in, you send a bit of audio file, you get the string back. But you still get, in the weirdest places, you get glitches. And you might tell this from YouTube when you have automatic captions. It's uncannily how good it is, but it still manages to fail at a consistently a consistent amount of times. So yeah, we're gonna use Mozilla Deep Speech for our next notebook, because it's open to use, and we like that because you can train it with your data. You can use the architecture and train it with your language. You don't have to wait for Microsoft or Google or anybody else to implement it for you. How do we make sure that we give the speech-to-text system the best chance of transcribing it? You will have to go in there and check the text. Again, we assume the fact that we're going to do it for 30 minutes of data and not 3,000 hours. What you need to do is you need to chop the recording up into small bits. So ideally, you'd want a phrase per clip. That's the best, and that's the easiest way for it to pick up context between them. You don't want to split in the middle of phrases. You don't want to keep more phrases, because there's no point to that. So we're going to split on silence. That's the best thing to do. You just determine areas where for more than 150 milliseconds or so, the decibel level is underneath the threshold. And you chop here, here, and here. And then you have your phrases. It's important from phrase to phrase because of volume changes and the rate of speech that people have and the difference. You need to make sure that you're choosing this right. Because if they're too long, you might not split at all or split into wide parts. And if they're too short, you split everywhere and you end up with short words, which sometimes are harder for TTS to pick up because it needs some context, or it uses some context around the word to make sure that it's one and not a homonym. So yeah, now we have our split up bits, and we're gonna send them through Mozilla. We're gonna get some text back. We're gonna change manually change the inputs that we figure out that are not working right. And another thing that we can do. So what we're doing after we get the text. We usually should run it through something that's called a forced aligner, which is at a smaller level of utterances. Like, can you tell exactly where this word in a phrase, right? I have prepare your text cuts. Do I know which bit of the audio file on the left belongs to the word text, right? I need the exact timestamp, because the finer the detail of data I give to Tacotron, the better will it be able to make sure that this bit of here was text and not mixed up with something else. So you do force align. We recommend Montreal force aligner. We tried multiple tools. They're horribly hard to get working, and I could not get this to work in Colab. But I'm just going to show it to you. It even does it at the level of phonemes. So for example, you feed it, you do feed it text, and you feed it the waveform, and it goes and looks on very interesting maths. What's the most likely association between how do you warp the text in order for it to fit nicely between, like, I know that there's a consonant here, a vowel here. It gives you the exact timestamps that you can feed back to the model. Again, I'm gonna fire up a workshop for you in just a second. If I can find the tab. There you go. I just need to make sure that you can see it. Yeah. So as I discussed with, we're going to ignore the fact with the thing with the speaker diarization, and that was also a bit out of scope for this specific Colab notebook. But what you want to do is you want to give it, and you can change this, by the way. Feel free to play around with the parameters that will be downstream for here. We picked a short address by Obama when
everybody who owns a car.
So he's the only one that's speaking in the videos, which is really good for us because we can just skip that first step and not have to load in memory the embedder again. But you see what's here, right? We're going to cheat now because somebody already, right? Somebody probably from the White House, a poor intern, had to be there and write down the script. The advantage of that is that with YouTube DL, we can check if there's an English subtitle there, and if there is, we can catch it in a VTT format. The VTT format, then we have an audio file and a text file. You remember how we start, right? We do have, and we already have timestamps, so we don't have to split on silence. Yeah, so you can do this for movies, you can do this for everything else. If you want to clone an actor's voice, subtitles is the way to go. What happens is if you run all of these bits, this is just making sure that we have an output folder in the shape of how you'd send them to Tacotron, right? So same names, text and labs, your long form text, you reading in the captions and parsing all of the timestamps. Yeah, let's see how we did.
Hi, everybody.
Perfect.
In the State of the Union, I laid out 3 areas we need.
Now we're missing a bit at the end, right? So do not rely on captions fully for this. The captions will get you probably the best text, or the text that the president had prepared to speak anyway. So the text will be on point. But sometimes the captions end up a bit earlier and cut into your text, or move words on the other side, which is obviously suboptimal. But still, it's a good starting point, right? You'd rather go back and say give me a bit more audio data and I'm going to cut it back because this will give you a very good data set. I can just feed this into Tachytron or into CurrentNJ's to do the home cook model on. And if I do this for 5, 6, 7 videos, we definitely have enough data to model his voice very accurately. We're also gonna load in deep speech. I really hope it's still loaded. So let's compare how the deep speech and split on silence method works. Again, you can find here the parameters for just wait 0.1 of a second to define the silence. Everything that's minus dBFS, minus 65 dBs will be treated as silence. And also to just throw that on top, a bit of logic that says if a chunk that you create is shorter than 2 seconds, concatenate it to the other ones. So we have reasonable amounts of time and speech in each phrase, right? So we don't cut in the middle of it. So before we did that, we would get 1 second of text, 0.8 second of text. But by doing the other thing, you can get some better phrases in here. Right. We just throw all of the chunks that we just made, that we just split on silence, and we know that they're complete because we split on silence and not on some arbitrary captions. We can send those audio files to deep speech and get our strings back.
Hi, everybody.
Unfortunately, here it drops the hi.
In the State of the Union, I laid out 3 areas we need to focus on
Actually, did all right for this one.
if we're going to build an economy that lasts. New American manufacturing.
Right. So you're gonna get the annoying bits like last versus lasts. You're gonna get a plural when you need a singular. You're gonna get stuff like this, and probably improper capitalization as well. But what's very important is that it works. And combining these two, right? You can also do, if you have subtitles, just run them for deep speech as well. Do a distance check on the transcripts, right? The possibilities are endless. The thing is, these are just some few tricks that we did employ to make our data sets for training our models. Going back to presentation in just a minute.
Should I start?
Yeah, I think so.
Yeah. Okay, cool. So in the next workshop, we will see some testing and evaluation. First, there will be some slides because it's a very interesting topic. When it comes to voice quality, testing the different results can become really challenging. At the first glance, one would think that there are simple methods to automatically quantify the quality of data, but in reality, it isn't. So the next work presented will be split in two. First, we will see some information about testing and evaluation of how we can measure speech quality and genuineness. And then in the workshop, we will actually fake a voice end to end using SV2 TTS method and use the speaker encoder to determine the probability of real fake audio file. But first, let's jump into testing. So we have some experience in voice over IP, and the first thought was, can we actually use something from voice over IP, which is mean opinion score, in order to evaluate how well a synthetic voice is perceived? There is a difference in the sense that in voice over IP, this score is used to compute the quality of voice over IP results sent over the networks and reflects also the internet network behaviors such as latency and jitter and delay and package loss. And yes, we realized by going through papers and research that most of them that are related to speech synthesis, they rate their results using MOS. So this is a very simple table of it's a subjective um, score. Uh, in voice over IP, there are codecs that do the encoding, decoding of voice into internet packets and have a general MOS score. And the codecs are classified depending on the performance into five different grades: 5 for excellent, 4 for good, 3 for fair, and what is below 3 is kind of annoying with the poor quality. And yeah, so with this in mind, we discovered that there's a deep neural network which is called MOSNet, and it was trained during a competition, which is a voice conversion challenge from 2018. The network was trained with a few thousand evaluation sets. Each consisted of 44 utterances, more than 113K human evaluations, covered 30K submitted audio samples, where each audio was covered by 4 different listeners, and each utterance has received a MOS ranging from 1 to 5, with lowest score of 1 and highest score of 5. And if we want to discuss a little bit more about MOSNet, what it does, it's MOS, well, it predicts the mean opinion score because it's deep learning. In the paper, it is proven that there's a good correlation between the predicted MOS and real MOS by using human rating. The input of MOSNet is a sequence of spectral features extracted from a speech utterance. There were different architecture tested for the predictor building, namely like CNN or BLSTM or a combination of the two. And yeah, it was okay, cool. Calin arăți așa. Okay, and if we go and see some results,
No
we
eminence has been making fresh complaints against your musketeers.
that's the real voice, and we will listen to the cloned voice.
Do
Which
you
is
know that His Eminence has been making fresh complaints against your musketeers?
And the quality of the cloned voice is obviously more robotic, and we are seeking for more naturalness, and thus we decided that maybe this solution doesn't work best for us, since the cloned voice receives the most score, which is higher. So through our research, we bumped into the concept of Siamese networks, that are special kind of neural networks that can be used to compare the distance between 2 images. And the network is composed of different CNNs. It's working in tandem on 2 different input vectors to compute comparable output vectors. The CNNs for each input image has the same structure and the same weights. Our CMS network was trained on black and white signatures, and the network is using a contrastive loss, which is done to compute the distance between images. And we will go more into details in the next slide. Where how did we get this idea? So we thought, okay, we have audio file, we have MOS, and maybe that's not good enough, or it's very like something against using MOSNet is that it's very hard to train. And we thought maybe we need something different. And what else do we have when it comes to audio files? We have the waveform, we have the spectrogram, and that's how we ended up thinking that maybe a Siamese network is going to help us. And we trained our network on forged signatures that can tell us if a signature is real or fake, with the same the same weights and the same structure. And then you have a base model and a head model, and using the loss you can decide what's the distance between the 2 images. And that's how we actually did it for our uh, detection of a fake speech, because it's a similar problem where we gave, well, not really the waveform, but rather the spectrogram. And in the following slide, we have some results. So these are 2 examples of spectrograms. Let's say the one above is the real one, and the one lower is the clone spectrogram. And the score is actually on the right side and is 0.02. And the distance is really small, which means they are really, really close to each other. And then if we compare the original with the same original, we see that we get a very small value, which is a default epsilon value. If you compare one original with a different original, you will get a higher value, a bigger distance. So the closest the distance between the images is to 0, the similar they are. The closer they are to 1 or even higher, it means that the images are not similar. And then we also thought that what is a cloned voice if not a forged voice? We all wanted to sound very natural, but at the same time, through our research, we thought of using maybe Resemble AI work that is developed for deep forged voices. It's a package. It has great capabilities such as diarization, the thing we saw when Calin presented, such as fake speech detection that predicts which audio are cloned or fake, and they have a Siamese-like behavior. You can visualize the embeddings of the utterances, close from the same speaker, far from other speakers. And yeah, we use this work as well to check if some speech is legitimate or forged compared to the similarity of possible forged speech to real speech. And as examples, what's with green is actually the real voice, and what's with red is the cloned voice of the same files. And we see that there's one miss. There's one cloned file that is considered to be real. And I think that, okay, now I have to.
I think that you need to let me stop sharing mine. Can you share yours now?
Yeah, just 1 second. So I move you guys here and I can share. And I share the entire screen. Right, screen 2.
With audio, if you
Entire screen, right?
with computer audio.
With computer. I almost forgot. Okay, sorry about that. Can you see it? Okay, I also tried to load. Let's see if we still have them. Okay, cool. So first we will do one-shot voice cloning. These are the steps that you need to clone a voice that has at least 5 seconds of data. And in order to do that, we will set up Quarantine J. Oh, how do I do? Go back. Okay, whatever. We will set up Quarantine J. I can see the code. Oh, yeah. Code? No. I don't know what to do.
The cell, I think you need to do control. Did you delete the cell?
No, I no longer have the code. Okay. It's like it moved this cell here.
Oh no, have you tried running it? Just press play.
Well, I've already run it. It takes a long time to preload it. Anyway, in this part, what we do is to get all the required libraries and things to work in GitLab, and then we also take the pre-trained files that are for the 3 main parts that were discussed in the in this presentation related to one-shot voice cloning. You remember the Spartan recipe for food, where you can take Quarantine J's work and actually apply and get a cloned voice. And then you check where you are, you go in your own folder, then you get the imports that you need. So the 3 main parts are the encoder part that creates the clusters of voices that have to be as far as possible between themselves. There is the synthesizer that I'm missing, no, that inputs characters and outputs spectrogram frames, and there's the vocoder as well that creates from spectrograms a waveform, an audio file. So first we load the pre-train that we need, then we define sample rate and functions to compute embedding of the speaker.
And making fresh complaints against your musketeers.
This is the voice we are going to clone. You will find it in the repo. Then we load the synthesizer, we load the vocoder, and then we have a new text that we are asking the lady to tell us. And we have a synthesize function where we synthesize using text and embedding, and using a vocoder, we recreate the waveform. And this is done here.
This is a voice cloning audio workshop. It is a great opportunity to learn new things.
Okay, so this was the first part. We will share as well the links so we can all have access to these collabs. And then we have the last slide from testing where we were looking into Forge versus Real Voice. This is also a work from Quarantine. I put them in my own repository because I wanted to give you access to the files, but you can go directly to Quarantine J. And basically here, what do you need? You need the required imports. You need to load and pre-process the audio files with real and forged data. Then you compute the embeddings of each speaker. You take 3 real embeddings at random and leave 3 others for testing. You compare all embeddings against the ground truth embeddings and compute the average similarities. You install the proper matplotlib version so it doesn't crash, and then you can plot it. And these are example of results. Again, with grain, it's like what's the natural and real voice, and here's what is cloned and fake. And the question is, why do we care if a voice is forged or real? And I will pass the hat to Radu that can give us more details.
So, why is it important to understand if a voice is forged or real? I don't even need a slide for that, but it helps.
Sorry, I'm trying my best.
Yeah, no problem. So, as you can understand already, this we're talking here about a pretty dangerous technology. If and when this is going to be perfect, then we'll have similar problems to the deepfake applications that we can see and freak out and give lots of food for thought to the dystopians. These kind of technologies have lots of interesting ethical implications, and the first one hinted by Anna was exactly the one that is about forging voices. So if we have to uh, if we make a very small imagination effort, then we can understand that forged voice can do lots of harm. And I've read recently one apparently I think this was a real story because it appears in many journals about CFO that received an order from his CEO by phone to transfer money into a private account, and he did that because he recognized the musicality of the and the voice, exactly the voice of his superior, and that was a huge scandal. That it was a large sum of money, and such a tool that would be able to distinguish between a fake voice and a real one would have been really useful. Then you can imagine that there is a potential of identity theft with all the implications that there are. Um, if we let these technologies free on the market. And there is also the case of Joe Rogan. If you look on the web, that's a famous podcast producer that has obviously lots of materials, audio materials on the web. So there was plenty of material to fake his voice. And there is a company who produced a short sequence where he announced that he's training a monkey team for a basketball or for a hockey championship. Therefore, some implications deal with the potential use of the personal data that we share, like our recording today. And another interesting and not so obvious implication is about putting the voice of dead people into different types of applications, and that's a problem because it's quite difficult to get the acceptance of the person. So how do we do to avoid using these technologies in a bad way? We can control, first of all, control access to voice cloning APIs. We can request the consent from, if you go back, please, request the consent from voice owners, and Microsoft has a good practice approach where if you want to clone your voice or if you want to let somebody else clone your voice, you need to record a specific text in which you introduce yourself and say, okay, I agree that my voice is cloned, and then only if that sequence is in the training batch, the cloning voice process can be run. And the third enforcement that I wanted to mention today is a way to include watermarks to help distinguish between synthetic and real voices. So instead of using these techniques that Anna explained, we could include this, embed this from the beginning, and have some kind of similar to documents or to images, these watermarks that can help distinguish that that's not a real voice. And moving to the next slide, there are three key takeaways that we would like you to leave this presentation with. Voice modeling deals heavily with non-textual factors, and that's maybe not so obvious, but as explained, there is the prosody, there are the accents, the cadence, all these things that are not implicitly related to the text itself. Then there is no free lunch, so there are always trade-offs that must be understood between the different approaches to voice synthesis and voice cloning. You've seen the three recipes that we defined. There is the fast food, the Spartan one, the gourmet at the other extreme of the scale, and in the middle somewhere the home cooked. So depending on how much data you have, how much computing power you can access, and how much time even you have, you can prepare a really good or suitable to the purpose voice. And finally, speech synthesis evaluation is highly subjective. This is not so easy as watching an image and understanding the pixels, the colors, the visual hints. Here we need more subtle ways to evaluate if a voice is close to the ground truth or not. So voice modeling, non-textual factors, no free lunch, and subjectivity of the speech synthesis. And I think this is all from our part. We're really curious to see if you have questions, if there are things that you suggest or you're interested in, and we still have time for a discussion if you are interested.
Yes, I think we're gonna share or at least I'm gonna share the first two, the two notebooks because they're in reverse order. Apologize for that, and the deck of slides with you at some point. I don't know, Amalia. How would we field some Q&As if there's any questions or discussions that anybody in attendance would like to have?
We need to synthesize a voice for the moderator. Well, anyway, we can be contacted also after the conference. Our emails or accounts are public. So if anybody has some specific question, we will answer.
Or if someone wants to try the home cooked meal and would like to use some of to train Tacotron at some point, the synthesizer part of it, or I don't know, I'm just saying. We can give some lead or help.
Yeah, I'd be curious to see what types of usage people think would be useful to give to these technologies. So if there are no questions, we have questions for the audience. Or we can also call it a workshop.
Pause. I
Let's
wonder
wait
if
for a bit.
anybody is listening or hearing us. Oh, okay.
I'm using the alternative technology, WhatsApp, to ask the organizers if they are there.
Hey, I'm back. Share my camera. Are there any other questions from the audience?
How can the audience address the questions?
Well, a gentleman said that he's digesting the information, so that's good. If we can help you digest
The home-cooked meal.
the home cooked meal.
No, okay, I couldn't seem to hear anybody. That was a great workshop. Thank you. Are there any questions from the audience for Anna, Calin, and Radu?
Calling once.
Oh, okay, so Voipo will be in touch. Excellent. Thanks so much for the workshop. And
Thanks everybody for joining.
see you later.
Okay, thank you.
Okay, thanks so much. Thanks for being part of Zodiacs. Bye.
See you.
Thanks for having
Bye-bye.
us.
See you later. Bye.